There is a story we tell ourselves, a warm and glowing story about our destiny among the stars. We tell it in films and in speeches from launch pads. We tell it to children with telescopes and to engineers in clean rooms assembling the next great vehicle of human ambition. The story goes something like this. We are a species born to wander, born to push beyond every horizon, and one day, when the pressure of our numbers or the fragility of our single world becomes too great, we will simply pack up the essential ingredients of civilization and pour them across the dark into another world. Mars, the rust-colored wanderer hanging in the inner solar system, has become the leading character in this story. It is close enough to feel reachable. It has a surface. It has a thin envelope of atmosphere. It has a day that lasts 24 hours and 37 minutes. And so the story says, with enough engineering, enough will, enough courage, we can make it home. I want to take that story and hold it against the cold, unblinking light of physical law. Not because I wish to diminish the extraordinary courage of the engineers and astronauts and dreamers who pursue that horizon. Their ambition is real and their achievement is staggering. But because the universe does not grade on ambition, it grades on mathematics. And when you read the mathematics of what Mars actually is, what it represents as a physical object in the context of deep time, the story changes completely. Mars is not a stepping stone, it is a ruin. And more than that, it is a mirror. It shows us precisely what happens to a planet when the invisible engines that make biological life possible wind down and go cold. It is a textbook written in frozen iron and stripped atmosphere, and the chapter it teaches concerns not the future of our species, but the hard physical ceiling that planetary mechanics places over any biological organism that tries to operate outside the specific conditions of its native world. Think of it this way. Imagine a submarine, not a military vessel built for shallow coastal waters, but a deep ocean engineering masterpiece, pressurized and sealed and designed to cruise through the crushing darkness of the deepest ocean trenches on Earth. The passengers inside live in warmth and breathable air. The hull absorbs pressures that would compress an unshielded human body to nothing in seconds. The vessel generates its own light, its own food supply, its own recycled atmosphere, and its own electromagnetic field to protect sensitive navigation equipment from the distorting pressures of the deep. Now imagine one of those passengers pressing their face against the porthole and looking out at the frozen, lightless ocean floor below. They see a rocky surface. They see what might be the geometry of a landscape. And they say, I want to go out there and build a city. The ocean floor is not a frontier. It is a death environment. And the submarine is not a vehicle for exploring the ocean floor without protection. It is itself the only reason the passengers are alive. The submarine is the survival technology. The ocean floor is simply the environment that makes the necessity of that technology absolute and permanent. Earth is the submarine, Mars is the ocean floor, and we are the passengers who have somehow convinced ourselves that pressing our faces against the porthole constitutes a plan. To understand why this analogy is not poetic hyperbole but rigorous physical description, we have to look at what Mars actually is in the language of planetary physics. We have to go beneath the surface, literally to the core of the planet and to the history written in its magnetic record. Every planet in our solar system carries within it a thermal inheritance from the violence of its formation. The accretion of rock and metal, the relentless bombardment of early planetary bodies, released enormous quantities of energy, heating the interior of each world to temperatures of thousands of degrees. Inside the Earth, that primordial heat combined with the radioactive decay of isotopes like uranium-238 and thorium-232 has sustained a molten iron outer core for 4.5 billion years. That molten iron is not simply a geological curiosity. It is the source of one of the most important protective mechanisms in the known universe. As the liquid iron circulates through convective motion driven by thermal gradients and the Coriolis effect of Earth's rotation, it generates a dynamo, a global electromagnetic shield, a magnetosphere that extends tens of thousands of kilometers into space, deflecting the continuous particle stream of the solar wind around our world like a bow wave in front of a ship. Mars had this. 4 billion years ago, Mars had a global magnetic field, a liquid core, and geological evidence suggests it had liquid water on its surface, and an atmosphere thick enough to maintain it. But Mars is smaller than Earth, and this fact, this simple dimensional reality, sealed its fate through a mechanism as remorseless as any equation in physics. The rate at which a planetary body loses its internal heat to the surrounding vacuum of space is governed by the ratio of its surface area to its volume. Surface area grows as the square of a planet's radius. Volume grows as the cube. This means that as a planet becomes smaller, its surface area to volume ratio increases, and it radiates its internal energy into space far more efficiently relative to its total thermal reservoir. Mars, with roughly half the radius of Earth, radiates its internal heat proportionally faster. Over the first billion to 1.5 billion years of solar system history, the Martian core cooled and solidified. The convective motion in the liquid iron ceased. The geodynamo fell silent. And with that silence, the magnetic shield collapsed. What followed was not dramatic or sudden, it was patient and absolute. The solar wind, that continuous plasma streaming outward from the sun at hundreds of kilometers per second, began directly interacting with the Martian upper atmosphere. Without a magnetospheric shield to redirect it, the solar wind ion picked the atmosphere atom by atom, a process called sputtering, stripping the lighter molecules from the top of the atmospheric column and accelerating them above escape velocity. Over hundreds of millions of years, the Martian atmosphere was sandblasted away. Air pressure dropped from what may have been close to Earth-like conditions to roughly 0.6% of Earth's atmospheric pressure. The water, unable to exist as a liquid under such pressure, either froze into the regolith or sublimated directly into space. The temperature swings became extreme. A world that may have once hosted running water became a freeze-dried, irradiated desert. This is not a problem that human engineering can solve. We cannot restart the Martian core. We cannot rebuild a geodynamo. We cannot reconstruct a magnetosphere around an entire planet with any technology that obeys the known laws of physics. The proposals for terraforming Mars, for seeding its atmosphere with greenhouse gases or deploying orbital magnetic shields, are proposals for treating the symptom while the fundamental disease, a dead planetary engine, persists and can never be reversed. Mars is geophysically dead. And because it is dead, every human being who stands on its surface stands in a radiation environment that human biology was never built to survive. Here is where the physics of Mars transitions from the grand scale of planetary magnetohydrodynamics down to something far more intimate and far more lethal. Galactic cosmic rays are not the gentle radiation you might imagine from the word. They are charged particles, predominantly protons and heavier atomic nuclei, accelerated to extreme energies by supernovae, pulsar, wind nebulae, and other violent astrophysical processes across the galaxy. They travel through interstellar space at velocities approaching the speed of light, carrying energies per particle that can reach 1 million times what any human particle accelerator has ever produced. On the surface of Earth, we are almost entirely protected from these particles by our magnetic field, which deflects the charged particles away, and by our thick atmosphere, which absorbs and scatters whatever penetrates the magnetosphere. The radiation dose from galactic cosmic rays at Earth's surface is negligible. On Mars, with no magnetic field and an atmosphere less than 1% as thick as Earth's, the surface is bathed continuously in these particles. Now, an engineer's first instinct is to build shielding. Pour enough rock or water or lead between the human body and the incoming radiation, and the problem is solved. But the physics of high-energy particle interactions transforms this instinct into something darkly ironic. When a high-energy galactic cosmic ray particle strikes a dense shielding material, it undergoes a process called nuclear spallation. The incoming particle, traveling at a significant fraction of the speed of light, collides with the nucleus of a shielding atom with enough energy to fracture it. This fracture produces secondary particles, fragments of the original nucleus, fast neutrons, pions, and an entire cascade of secondary radiation. The denser and thicker the shielding material, the more spallation products are generated. A wall of dense rock or metal, rather than stopping the radiation, transforms a single energetic incoming particle into a spray of secondary particles radiating in all directions, including directly back toward the inhabitants. This is not a solvable engineering problem within the constraints of chemical propulsion and mass budgets. The only effective mitigation against galactic cosmic rays involves either the enormous mass of an entire planetary magnetic field and thick atmosphere, both of which Mars lacks entirely, or a configuration of shielding optimized through extraordinary precision that still provides only partial and temporary protection. Long-term human habitation on Mars means long-term cumulative radiation exposure that exceeds safe biological thresholds within years, not decades. The engineering does not merely fail to solve the problem. For certain geometries and shielding materials, the engineering actively amplifies it. But assume for a moment that we somehow solve the radiation problem entirely. Assume a perfect habitat, a perfect shield, a perfect pressurized environment. There is still a third sentence being written by physics, one that operates not from outside the human body, but from within its own cellular architecture. The human skeleton, cardiovascular system, and the regulatory mechanisms of cellular division were shaped by 4 billion years of biological evolution in a one-gravity environment. Every structural protein, every feedback loop in the cardiovascular system, every mechanism for calcium regulation in bone tissue is calibrated to the specific loading conditions imposed by Earth's gravitational field. Mars offers 38% of that field, and that difference, which sounds modest, is physiologically devastating over the timescales that permanent habitation would require. In microgravity environments aboard the International Space Station, we have measured bone mineral density loss at rates approaching 1 to 2% per month in load-bearing skeletal structures. The body, no longer required to support its full weight, systematically disassembles its own skeleton through a process of osteoclastic resorption that outpaces bone-building osteoblastic activity. Martian gravity would slow this process relative to microgravity, but would not stop it. Over years, the skeletal structure would become measurably compromised in ways that are not fully reversible even upon return to Earth gravity, and for permanent residents, there is no return. Cardiovascular fluid dynamics in a lower gravity environment shift the distribution of blood and lymph toward the upper body, increasing intracranial pressure and compressing the optic nerve, a phenomenon documented in long-duration spaceflight as vision impairment that, in some cases, becomes permanent. The muscle mass required to maintain cardiac output in a one-gravity environment is larger than what Mars would demand. And without deliberate and exhausting countermeasures performed for hours every single day for the rest of an inhabitant's life, the cardiovascular system shrinks and weakens progressively. Cellular division itself is altered in low-gravity conditions with documented changes in gene expression, cell signaling, and immune function that compound over time. A human being on Mars is not thriving in a new environment. They are dissolving slowly, their body dismantling the infrastructure built for a world it can no longer sense beneath its feet. And so we return to the submarine, and we see it now with total clarity. The submarine is not a luxury. It is the only thing between the passenger and instantaneous death. Earth, with its convecting mantle and its liquid iron core and its towering magnetic shield and its thick layered atmosphere,